Good day everyone. So we are done with the lesson 2, which is the number system. As we all know, number system represents number. It is also called the system of numeration and it defines a set of values to represent a quantity. So let's proceed to lesson 3, which is the number system conversion. The number system conversion is integral to the functioning of computers and digital systems. It facilitates data representation, arithmetic operations, memory addressing, data encoding, networking, debugging, and algorithm design. It is the conversion of number of one base to a number of another base. We will learn the conversion of one base number to another base number, considering all the base numbers such as decimal, binary, octal, and hexadecimal with the help of example. So here, the following number system conversion methods are explained. So we have binary to decimal number system, decimal to binary number system, octal to binary number system, binary to decimal, binary to octal number system, binary to hexadecimal number system, and hexadecimal to binary number system. And also, we have the general representation of number system, so which is the decimal number, which has the base of 10 with a number of 10, binary number which has a base of 2 with a number of 2, octal number with a base of 8 with the number 8, and hexadecimal number which has a base of 16 with a number of 16. And before we proceed to the number system conversion, let me introduce first the MSB and LSB. The MSB stands for the most significant bit, and the LSB stands for the least significant bit. So let's proceed to our topic. As you can see guys, there's a number system conversion table. So we see the binary number, the octal number, decimal number, and hexadecimal number. So the binary number, we have the first number, which is the 40, which is 0, 0, 0, 0. And the last number, we have 1, 1, 1, 1. And in the octal number, we have 0, 1, 2, 3, 4, 5, 6, 7. So we don't have 8 because it represents the octal number. 11, 9, 10, 11, 12, 13, 14, 15, 16, 17. And in decimal number, we have 0, 1, 2, 3, 4 up to 15 number. And last is the hexadecimal number. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. So the letters guys represents the 10 to 15 number. So A represents the 10, B represents the 11, and so on. So let's proceed to the conversion from one base to another. So decimal to other bases. Converting a decimal number to other base is easy. We have to divide the decimal number by the converted value of the new base. So decimal to binary number. Suppose if we have to convert decimal to binary, then divide the decimal number by 2. So of course, the base of decimal is 10. So in order to convert the decimal into binary, we need to use the base of the binary number, which is the 2. So let's deepen our understanding. The given example. So example 1. Convert 25 to the base of 10 to binary number. So instead of using the base of the decimal, we need to change it to the base of binary number. So instead of 10, we need to use the 2. So as you can see there in the table, you can see the operation, the output, and the remainder. So let's start with division, or let's start with dividing the given number, which is 25. So 25 divided by 2 is equal to 12, and the remainder is 1. So how did we come up with the remainder of 1? So we come up with the remainder of 1 because if we divide the 25 into 2, the answer would be 12.5. So because we have one decimal, 0.5, so our remainder is 1. And let's divide the output of 12, which is 12 divided by 2 is 6 with a remainder of 0, and 6 divided by 2 is equal to 3 with a remainder of 0, And 3 divided by 2 is equal to 1 with a remainder of 1. So how did we come up with the 1? It's because if we divide the 3 into 2, the answer would be 1.5. So because we have 1 decimal, we can also have 1 remainder. So that's our remainder 1. Then 1 divided by 2 is equal to 0 with a remainder of 1. So if we divide the 1 with 2, the answer would be 0.5. So because we have 1 decimal or 1 remainder, which is the 0.5 or the 0.5, so that's our remainder, the 5. So therefore, from the above table, we can write the conversion of decimal to binary number is 11001 with a base of 2. So that's how we convert the decimal into binary number. So again, let's always remember that we should start first with the lowest or the least significant bit up to the most significant bit. So we write 11001 and to the base of 2. So that's our answer. Okay, let's give another example to better understand the conversion of decimal to binary number. So let's start with the given number, which is 339. So how can we convert this 339 into binary number? So let's start first with 339 divided by 2 equals was 9 and the remainder of 1. So why do we have a remainder of 1? It's because if we divide the 339 into 2, the answer would be 169.5. So because we have 1 decimal, we need also to put 1 remainder because we have 1 remainder, which is the 0.5. Then second is we need to copy this 169. So 169 divided by 2 is equal to 84 with a remainder of 1. Because if we divide 169 into 2, the answer would be 84.5. So we have 1 remainder, so we need to put 1 remainder here. Then copy the 84. Copy the 84 and divide it with 2. Then the answer would be 42 with the remainder of 0. Because if we have the remainder of 0, because if we divide 84 into 2, the answer would be 42. There is no decimal or remainder. Then copy the 42 and divide it into 2. The answer would be 21 with the remainder of 0. Then follow 21 divided by 2. The answer would be 10 with the remainder of 1, because if we divide the 21 into 2, the answer would be 10.5. So there is 1 remainder, so we need to put the 1 here, remainder. Then followed by 10 divided by 2 is equal to 5. We have the remainder of 0. Then 5 divided by 2 is equal to 2, which has a remainder of 1, because if we divide the 5 into 2, the answer would be 2.5. So we have 1 remainder, which is 0.5. So the answer or the remainder would be 1. Then 2 divided by 2 is equal to 1 with a remainder of 0. Because if we divide 2 into 2, the answer would be 1 only. And 1 divided by 2 is equal to 0, of course. And we have the remainder of 1, because if we divide 1 to 2, the answer would be 0.5. So we have 1 remainder, which is a 0.5. So how can we convert this into binary number? So let's put here. Let's start with the least significant bit to the most significant bit. So here, LSB, LSB. So let's start here in the lower part, which is we have 1, 0, 1, 0, 1, 0, 0, 1, and 1. So this is our binary number. So this is our answer. 1, 0, 1, 0, 1, 0, 0, 1, 1. So it's easy, guys, if you understand it. So let's proceed to the decimal to octal number. So to convert decimal to octal number, we have to divide the given original number by 8 such base 10 changes to base 8. So of course we have the decimal or the base of the decimal is 10. We need to change it to the new number or to the new base, which is octal number have the base of 8. So we need to use the base of 8. So let's deepen our understanding with the giving example. So convert 128 with a base of 10 to octal number. So instead of using base 10, we need to use the base of the octal number, which is the 8. So as we can see, we see the operation output remainder. So of course, you probably know how to compute or how to solve the given problem. So 128 divided by 16, 128 divided by 8 is equal to 16 with a remainder of 0. And we need to copy the 16 and divide it into 8. And 16 divided by 8 is equal to 2 with a remainder of 0. And last is 2 divided by 8 is equal to 0 with a remainder of 2. So how did we come up with the remainder of 2? So if we divide the 2 into 8, the answer would be 0.25. So because there are two decimals or there are two remainders, so the possible number that we put in the remainder is 2 because we have two decimals or we have two decimal number, which is the 0.25. So therefore, the equivalent octal number is, of course, we need to start with the least significant bit up to the most significant bit, which is the 2, 0, 0 with the base of 8. So that's how we convert decimal to octal number. Okay, let's proceed to decimal to hexadecimal. Again, in decimal to hexadecimal conversion, we have to divide the given decimal number by 16. Because as we all know, hexadecimal has the base of 16. So we need to use it as a base. So let's deepen our understanding in the given example, which is the convert 128 with a base of 10 to hexadecimal. So instead of using the base of the decimal, we need to use the base of the hexadecimal, which is the 16. So 128 divided by 16, so we have 8, and the remainder is 0 because if we divide the 128 into 16, the answer would be 8. But if we divide the 8 into 16, the answer would be 8 divided by 16 is equal to 0.5. 0.5. So because it's 0.5, we need to times it to the base, which is the 16. So we need to multiply. So 0.5 times 16 is equals to 8. So that's how we come up with the remainder, with the last remainder of decimal to hexadecimal conversion. So as you can see, the equivalent of hexadecimal number is 80 with a base of 16. Of course, we always need to start with the least significant bit up to the most significant bit, which is the 8 and 0. So that is the answer that is the conversion of decimal to hexadecimal. Okay, let's proceed to other base system to decimal conversion, which is the binary to decimal. So in this conversion, binary number to a decimal number, we use multiplication method in such a way that if a number with base n has to be converted into a number with base 10, then each digit of the given number is multiplied from MSB or most significant bit to LSB or least significant bit with reducing the power of the base. So let's understand it with a given example. So example 1 is we need to convert the binary number, which is 1101 with a base of 2, into a decimal number. So now, multiplying each digit from the most significant bit to least significant bit with reducing the power of the base number 2. So, as you can see in the example, we have the given number of 1101. So, in order to solve this, we need to put first the first digit here. So we need to times the first digit, which is 1, with the base, which is 2. Because we have binary, because the base of the binary is 2. So plus second digit is 1, so we need to copy it here. So 1 times 2 with the base, plus third digit is 0, so 0 times 2, plus last digit is 1, so we need to copy it here, 1 times 2. So this 2 here is our base of the binary. So before we multiply it, we need to use the multiplication method. So we need to put first the power of this solution. So we need to start here with the list. So we need to put 0, 1, 2, and 3. We need to put power of in each of the base. So we have 4 base here. So 1, 2, 3, 4. So we need to start with 0, 1, 2, 3. So after that, after putting powers, let's multiply it all. So 1 times 2 is equals to 2 times 3. 2 times 2 equals 4 times 2 is equals to 8. 8. Of course, wait a minute. 8. So we have 8 plus 1 times 2 is equals to 2 times 2 is equals to 4. Plus 0 times 2, of course, automatically 0. 0. Plus 1 times 2 is equals to, no, we need to copy only the 1 because we can't multiply it if the base has the power of 0. So the number here will automatically put in this place, in below. So after we multiply the solution, we add this. We need to add this to come up with the binary number or the decimal number. So 8 plus 4 is equal to 12, plus 0, 12, plus 1 is 13. So this is our decimal. Therefore, the binary number, which is 1101 with a base of 2, has the decimal number of 13 with a base of 10. So this is our decimal number, which is 13 with a base of 10 because the base of our decimal is 10. So this is the answer. Okay, let's proceed to octal to decimal. So to convert octal to decimal, we multiply the digits of octal number with decreasing power of the base number 8, starting from MSB to LSB and then add them all together. So let's understand with the given example, which is convert 22 base of 8 to decimal number. So we have 22 here, 22. So just like here, just like the example here, we need to start first with the first digit of the given number, which is 2. So 2 times, of course, we have octal, so the base of octal is 8, so we need to put 8 here. So 2 times 8 plus the second digit of the given number is 2. So 2 times 8 is this. So we shouldn't we shouldn't forget the multiplication method, which is the power of. So we shouldn't forget to put power of in the base number. So let's put 0. Let's start always with 0. Then 1. So this is how we put the power. Then after that, after putting all the power and after arranging the given number, we multiply this 2. So 2 times 8 is equals to 16 times 1 is 16 plus 2 times 8 is, of course, rules is that if the base has a power of 0, we don't need to multiply it. So the 2 here is still 2. Nothing changed. So that's how we compute the given number. So after we multiply, let's add them together. So 16 plus 2 is equals to 18. Therefore, the octal number of the conversion of octal number of 22 base 8 to decimal is 18 with a base of 10 because it's decimal. You shouldn't forget that. So that's how we compute the octal to decimal. And let's proceed to our last topic, which is hexadecimal to decimal. So let's understand better with the given example, which is the convert 121 with a base of 16 to decimal number. So again, we have the given number of 1, 2, 1. So first, let's start with the first digit of the given number, which is 1. 1 times, of course, hexadecimal. So the base of hexadecimal is 16. So we need to use the base of 16. Then plus the second digit, 2 times the base number plus last digit, which is 1. 1 times the base of 16. So we shouldn't forget to put the power. So let's start with the 0, 1, and 2. So therefore, after we complete the multiplication method, we need to multiply it. So 1 times 16 is equals to 16. 16 times 16 is equals to 256. 256 plus 2 times 16 is equals to 32. With 32 times 1 is still 32. So 32. Plus 1 times 16, of course, if the base has a power of 0, we don't need to multiply it. Instead, we copy the given number here. So which is 1. Then after we multiply all, let's add this result. This. So 256 plus 32 is equals to 288 plus 1 equals to 289. Therefore, the conversion of hexadecimal number of 121 into decimal is that 289 with a base of 10 because, of course, it's a decimal. I mean decimal number. So we convert the hexadecimal to decimal, so our base should be decimal. So the base of the decimal is 10. So that's how we compute the conversion of hexadecimal to decimal number. So that's all, and thank you. So before we end this lesson, let me give you an activity of the conversion of number system. So as you can see in the PPTs, that's your activity. And before we end this module 2, which is computers in our daily life, let me give you an application that you need to answer, and that's it. Thank you for your time.